Okay, so here let's take a look at the sample problem. So yeah, so you can see here we have a battery and a switch and a switch and a capacitor. Okay, so so you can simply imagine we try to charge the capacitor. So it says the switch S is closed to connect the uncharged capacitor with the capacitor C to be 2.5 microfarad to the battery of the potential V equals 12 volt. The lower capacitance plate has a thickness L, 0.5 centimeter. Okay, so this thickness is not really important in this problem. And then the phase, yes, I mean the area of the phase is A to be this value, and it consists of copper, in which the density of conduction electron is N. So this is the electron density in a unit volume. So blah blah blah, electrons per meter cube. Okay, from what depth within the plate must electron move to the place phase as the capacitor become charged? Okay, so actually it tells you some real physics, like yeah, before I just tell you that all the charge in the conductor will go to the surface, but actually there should be a thickness, but this problem tells you that the thickness will be really small. As much as there should be some electron density, the electron still occupies some volume, but yeah, so and it really depends on this density really depends on material. For this one, this value is for the copper. Okay, so yeah, so let's see. So first of all, let's see how many charge should be on the plate, because it's already give you the value of the capacitance and also the voltage. So you can simply imagine we can be able to calculate Q equals CV. So we have C to be 0.25 times 10 to negative 6, and then times 12. Okay, so this value. Okay, so Q will be 3 times 10 to negative 6 coulomb. Okay, so this is the first step, and then next we would like to consider how many electrons are there, because this one is the density, so it counts how many electrons rather than the charge amount. So we would like to calculate the number of electrons, which is 3 times 10 to negative 6 over 1.6 times 10 to minus 19. Okay, so this is the charge amount, and then divided by the elementary charge, it becomes a number of electrons. So this number is 1.87 times 10 to the 13 electrons. Okay, so in that case, we would consider there are so many electrons on the surface, and then it tells you that the density, like the maximum density, can be this value. So we can be able to calculate like N equals, this is the density times the cross-section area times the thickness. Okay, so this is the volume times the charge density. The volume charge density will be the number of electron. Okay, so here we would like to calculate D. We will like to calculate D. So all the value we already know. We know N, we know A is here, and then we also know N. So finally we would like to calculate D. So D will be capital N over N times A. So N is 1.87 times 10 to the 13 power, and N is this number, 8.49 times 10 to the 28th power, and then times cross-section area is 2 times 10 to negative 4 power. Okay, so this one is 1.1 times 10 to negative 12 meter. Okay, so you can imagine this is really small, really small. Okay, so this is like picometer. So when we really consider like so recently, you know, the chip, the news about the CMOS chip, so they talk about how many nanometer is, so 1 nanometer is like 1000 picometer, and they talk about 1 nanometer, 2 nanometer, so like like this, like a transistor, maybe you don't really need to know that it's just like a semiconductor circuit. Yeah, so in that case, when they talk about what kind of technology, this one is the width, this one is the length of the MOS transistor, and then if it is like a 28 nanometer, then this is like 28 nanometer. If it is like a 1 nanometer, 2 nanometer, then if within 2 or 3 nanometer, there only be several atoms like that. So in that case, this thickness is really small. So usually we just consider all the electron will go to the surface of a conductor. Yeah. Okay. So next, we talk about parallel and series capacitor. So for the first one is the parallel capacitor. It will be easy. So in conclusion, it is just like you add them together for the parallel capacitance. Okay, so the idea is like if we have parallel capacitor, parallel means 并联. 并联, okay. Parallel means 并联. Okay, so in that case, which means that the bottom plate connect with bottom plate, connect with bottom plate. The top plate connect with the top plate, connect with the top plate. The bottom plate connect with the bottom plate, connect with the bottom plate. Yeah, so they are called parallel capacitance. For parallel capacitance, of course, for capacitance there are 3 variables: Q, C, V. Of course, C are not sharing variable. It can be C1, C2, and C3. So these are not share variable. So for parallel and series capacitance, one of it is sharing Q, one of it is sharing V. For the parallel capacitance, actually they are sharing V rather than sharing Q. So in that case, as much as all the top plate connecting to the positive node of the battery, and then all the bottom plate connecting to the negative node of the battery, so all of them are V. Okay, so sometimes I will draw plus negative, which means that this node have a higher potential than the bottom node. So to specify, this node, the potential at this node minus the potential at this node to be V. Okay, so for parallel capacitance, this is the sharing variable. These are the sharing variable. So we won't have V1, V2, V3. We all the way have V for the parallel capacitance. Sharing variable. So in that case, we have Q1 equals C1V, Q2 equals C2V, Q3 equals C3V. And then we just try to add them together. We have a Q equals Q1 plus Q2 plus Q3, and then C1 plus C2 plus C3, because V is a common factor, so we can just factor it out. We have a summation of C times V. Okay, so and in that case, such as we have here, and then we consider the equivalent capacitance. Equivalence means 等效, which means that if we would try to replace all these three capacitors by only a single capacitance, CEQ. CEQ is the equivalent capacitance. Okay, and then it should look everything the same. So this Q should be the total Q, Q1 plus Q2 plus Q3. And then if we don't change the V, then Q over V and then Q1 plus Q2 plus Q3 over V shouldn't change at all. So which means that if we have an equivalent capacitance connecting to the same battery, we should have C equivalent equals Q over V. Q over V. And then here, if you look at the extreme left and the extreme right, we can also have Q over V to be C1 plus C2 plus C3. So in that case, we can just plug in this one here. So we have C1 plus C2 plus C3, which means that we have C equivalent to be C1 plus C2 plus C3. That's why we just try to add the capacitance together for the parallel capacitance. If we have N capacitance in parallel, then we just add all the capacitance together. So it is easy. And then for the next case, it will be capacitance in series. So this is 串联. Okay, so 串联. Okay, so just now I also mentioned QCV. C cannot be shared. Okay, so for series, Q is the sharing variable. Q is the sharing variable. Sharing variable. Okay, so what does it mean? Here, for series capacitance, it means that for the first one, top plate, bottom plate. So for the bottom plate of the first one connecting to the top plate of the next one, and then the bottom plate of the next one connecting to the top plate of the next one, and then finally they just chain up to be a line like this. Okay, so and then the last one, the bottom plate of the last one connecting to the battery, the top plate of the first one connecting to the battery. So it forms a loop like this. Okay, so in this case, that's why the Q is sharing, because if you don't apply the battery yet, there shouldn't be any charge accumulate in between. There shouldn't be any charge accumulate, no charge at all if there is no battery. So there should be no charge, no excess charge. Okay, so if you apply the battery, then there will be some charge, but as much as the charge is conserved, then there should be positive Q, negative Q, and then similar here, negative Q, positive Q. So here we should have negative Q and positive Q. So in that case, as much as here we have conservation of charge, but within the capacitor, this one, and this one, they should have the same charge amount. They should have the same charge amount. That's why we should have the sharing variable Q rather than V. So here we have a Q over C1 V1, Q over C2 V2, Q over C3, Q equals C2 C3 V3. So in that case, we should have another relationship. This one is called the Kirchhoff Voltage Law. Kirchhoff Voltage Law. We will talk about it later in chapter 27, but maybe you should have learned it in high school physics, maybe, I'm not sure. But yeah, usually I will just call it KVL. And another one is called Kirchhoff Current Law. Kirchhoff Current Law, C-U-R-R-E-N-T, Current Law. So in short, it will call it KCL, not the KCL in the chemistry class, not the potassium chloride, This is Kirchhoff Current Law in the circuit theory. So here we will use a KVL here. KVL means if you start from a point in a circuit, and then we go up here. So we go from 0 volt to V, and then go back here, plus minus. So it go down by V1, go down by V2, go down by V3. If you just go a loop, the voltage change should be 0 for a complete loop. So which means that here, this is from negative to positive, so we have V. But here we are go from positive to negative. So it is like negative V1 and then positive to negative, minus V2 minus V3, minus V2 minus V3 to be 0. So it's so-called the KVL. So if we just move these terms over, then we will have V equals V1 plus V2 plus V3. And then we try to plug in these three equations here. So Q is the common variable, is the common factor. So we can factor it out, and then the remaining thing is 1 over C1 plus 1 over C2 plus 1 over C3. Okay, so similarly, we will try to replace all these three capacitors by a equivalent capacitor. Okay, so similarly, we have a CEQ equals Q over V. And then here, if we just look at here and here, you can also have Q over V to be 1 over C1 plus 1 over C2 plus 1 over C3. Okay. So you just plug in this one to here, which means that you get CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. Or if you just take the reciprocal of both sides, you will have reciprocal of CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. If in general you have n capacitance in series, then you just take the reciprocal of all the capacitance, add them together, and then take the reciprocal again to become the equivalent capacitance. Okay, so yeah. So these are the two situations. One is the parallel one, which is easy. You just add them together. For the series one, you take the reciprocal of the capacitance, add them together, and then take the reciprocal again to become the equivalent series capacitance. Okay, so next we talk about the energy stored in an electric field. So which means that originally, if a capacitor is empty, okay, then finally it changed to with some positive Q and negative Q. Then you should do some work to do so. The work should be done by the voltage source or the battery, the voltage source or the battery to do this work. So it consumes power. Consume energy. Okay, so the energy stored in the E field or stored in the capacitor is like this one. So U equals integration of du, and then du. If you still remember, in chapter 24, we have U equals Q times V or V times Q, which should be the same. And then here we try to put in the charge one by one. So it is like du equals V times dq. Put it in one by one, and then we try to integrate it. Okay, so here we have a V dq prime, because the upper bound will be q, so we just put a prime here to distinguish this one with this one. Okay, and then we have a c equals q, c equals q over v, q equals cv, which means that a q equals cv, we have a V equals Q over C. So we can just put in this one to here. So we have a Q prime over C rather than Q. So we just put prime here. Okay, so Q over C and then dQ. So C is a constant. We can just put it out, and then integrating Q prime dQ will be the square and then over 2. So finally we have Q squared over 2C. So this is how we can derive this equation. And then usually when we try to use this one, usually I will use this one or remember this one. Okay, the idea is like we try to eliminate Q, especially for circuit theory. We seldom consider the charge, seldom consider the E field. We usually only consider the voltage, RLC value, something like that. So we just try to eliminate Q by substituting Q equals CV. So we have C squared V squared over 2C. So it turns out to be 1 over 2 CV squared. 1 over 2 CV squared. So which means that the energy stored in the E field of a capacitor is related to the potential difference square, and also the C, the capacitance value. If it is larger, it can store more energy. Okay, so yeah. And then this one is called the energy density per unit volume, potential energy per unit volume. Okay, we will use this later in chapter 32 or 33, chapter 33. When we talk about the EM wave, we will use this later. But yes, I seldom use this one. Just need to use this one to explain the energy stored in the E field and the B field. The B field, like the magnetic field, in the EM wave. Okay, so this is like the total energy in the unit volume. So I do not try to prove it generally. I just try to verify it using the parallel plate capacitor, like this. So here we just verify for parallel plate capacitor, parallel plate capacitor. Okay, so we have small u is the energy density, will be the total energy divided by the volume. So for the parallel plate capacitor, the volume is actually, this is the volume. The volume will be this is the volume. Yeah. Maybe I just try to write a volume equals A times D. A is the cross-section area times the D is the distance between the two plates. Okay, so this is the volume. So U over A times D. Okay, so here we already have U to be 1/2 CV squared. So we put it 1/2 CV squared over A times D. Okay, so here we can just put it as 1 over 2AD, and then times, for the parallel plate capacitor, C is epsilon naught times A over D. So this is C, and then V square we can just leave it there. Okay, so in this case, we can do some cancellation. We can cancel this A with this A. So altogether, we have 2D, which means I mean we have D squared, and then we have V squared. So we can just put them together. We have epsilon naught over 2, and then we have V over D quantity squared. And then for V over D, as much as E is uniform, so we have 1/2 epsilon naught E squared. So this is the energy density stored in the capacitance, or stored in the E field. So 1/2 epsilon naught is a constant, and then which means that this energy density is proportional to the magnitude of the E field square, the square of the magnitude of the E field. So if the E field is stronger, then it stores more energy. Or in the other way around, you can consider, like, if you would like to generate a stronger E field, you need more energy to do so. Okay, so here let's see a sample problem. So it sets an isolated conducting sphere whose radius r is this value and has a charge q. How much potential energy is stored in the electric field on this charged conductor? what is the energy density at the surface of a sphere? At the surface of the sphere. Okay, so here let's calculate C. Okay, suppose it is an isolated conducting sphere, which means that C should be 4 pi epsilon naught R. And then we would like to calculate the potential energy. We would like to calculate the potential energy, which means that the potential energy is 1/2 Q square over 2C. Q square over 2C, because it just gives you Q, so we can just plug in Q and also put in C there. So it is like Q square over 2C. So altogether we have 8 pi epsilon naught R. Okay, then we can plug in all the numbers. So Q is first one we have this one. So it is like 8.99 times 10 to the 9th power over 2. And then times Q square is 1.25 times nanocoulomb. Nano is 10 to the minus 9th power. And then square over R is 6.85 centimeter. So 0.0685 meter. Okay, so this value will be 1.03 times 10 to negative 7 joule. Okay, so this is for question A. For question B, what is the energy density at the surface of the sphere? Energy density at the surface of the sphere. So for the so actually this is not this one divided by the surface area, because this is the total energy stored in the whole capacitor. So what we need to consider is that U equals 1/2 epsilon naught E squared. And then for a spherical capacitor, we also have E equals 1/4 pi epsilon naught times Q times R squared, because we consider at the surface of the sphere, so which is capital R. So we can put this one into here. So altogether we will have 1/2 epsilon naught, and then E squared will be 1/16 pi square epsilon naught square, and then times Q square over R to the 4th power. So altogether we will have Q square over 32, and then epsilon naught and epsilon naught can be partly cancelled, and then we still have pi square epsilon naught R to the 4th power. So we can plug in the values. Q is 1.25 times 10 to the negative 9th power quantity square over 32 pi square, and then epsilon naught is 8.85 times 10 to negative 12, and then times R is 0.0685 to the 4th power, like this. So this is 25.4 times 10 to negative 6 joule per meter cube. Okay, or you can just write it as 25.4 microjoule per meter cube. Okay, so both of it are okay. You can during the quiz or exam, you just need to write one is okay. You don't need to write both. Okay. So next, we talk about the capacitor with a dielectric. So just now I mentioned that if you need to increase the capacitance of a capacitor, you can just increase the cross-section area or just make the distance between the two plates smaller. Okay, so this is the third method to make the capacitance larger. So here we try to put something inside the capacitance like a sandwich. So if the space between the plate and of a capacitor is completely filled with a so-called dielectric material. Dielectric material. In Chinese it is called 电介质. 电介质. Okay, so the capacitance C in vacuum or effectively in air. So the electrical characteristic in the vacuum or in the air are quite similar. Although precisely it is a little bit different, but it is really close. So in physics level, general physics levels, then you just need to consider the electrical characteristic in the vacuum or in the air are almost the same. Okay, so it's multiplied by the material dielectric constant kappa. So this is not K, this is kappa, a Greek letter, which is a number greater than 1. Yes, so this one is very important. So this number is always greater than 1. Greater than 1, because in other material the speed of light will be just lower than the speed of light in the vacuum. Yeah. That's why the ultimate speed in the universe is the speed of light. You cannot make anything move faster than the speed of light. Yeah, so that's the hypothesis in the relativity. 相对论的一个假设就是光速是恒定的。当然在真空或者是在空气里面是固定的，无论在任何的惯性坐标系里面都是固定。Okay, so that's very interesting. Yeah, but yeah, in this semester we will not able to cover the special relativity. So if you have interest, you can just check it on my YouTube channel. Actually the mathematics for the relativity is not difficult. You just only need to know the geometry in high school geometry or a very little bit trigonometry. Then it's good enough to go. So yeah. So the mathematics is really easy, but the idea is hard to imagine. Okay, so just go back to here. So we try to put something called a dielectric material inside the capacitor. So here we have two experiments. So let's take a look at the left one first. So here we have a battery connecting with a capacitor. Of course it should be like something like this. Okay, somehow broke it. Okay, it should be the complete loop. Okay, so at the very beginning we have the battery, we have the capacitor, so there will be some charge. And then here we try to put in some dielectric inside the capacitor. After putting in the dielectric, the charge becomes larger. The charge becomes larger. We don't really change the potential difference of the battery or the voltage of the battery. Okay, and it makes the charge accumulate, become more. Okay, so for this case V is constant, and then here Q increase, and then for the right case, okay, it's also connected them properly. Okay, here we don't try to change the battery. So here the setup is like we try to we try to charge it with the charge Q. Here, it remains Q and negative Q. And then we try to disconnect the battery. So there is no path for the charge to go. So the charge remains Q and negative Q. And then we try to use a voltage meter to measure the voltage here. So this is just a voltmeter. Voltmeter 电压计就是它只是用来测量有多少电压用的。So this is just a voltmeter. This is not a battery. So for the initial case, the voltage is like this. And then after plugging in the dielectric inside the capacitor, okay, of course the Q doesn't change because there is no current going through. Okay, so the charge doesn't change at all. So here it says Q is a constant, but here you can see volts. The voltmeter, the voltage becomes smaller, which means that here V becomes smaller. So based on these two situations, you can imagine C equals Q over V. For the left case, V doesn't change, Q increase, which means that C increase. So C increase. For the right situation, Q doesn't change, V decrease. Q doesn't change, V decrease. So also C increase for both cases, which means that for both cases, if we just plug in the dielectric, the result is that you make the capacitance become larger. Okay, so here, this slide try to show you some hardcore physics. So you can just try to understand, but yeah, if you don't really understand, then it's still okay. So just try to feel like listening to a story. So here it's just an atomic view of the dielectric. Okay, so the dielectric is like, if you don't apply any E field to it, then the dielectric is like there are many dipole. There are many dipole inside the dielectric. If you don't apply any E field to it, then the dipole will point to different direction. Just randomly point to different direction. And then it will not generate any E field at all. So this one just said, if you don't apply any initially, electric E field inside this non-polar dielectric slab is 0. If you don't apply any E field to it, it will not generate E field either. Okay, but if you try to apply some E field, apply some external E field, the external E field is generated by this one and this one. This one is like the two parallel plate. If you try to apply some E field, so of course this is parallel plate, and then there will be some E field pointing from left to right. This is a positive side, this is the negative side. The E field point to the right side. If you provide some external E field to it, then you will make all the dipole align. Okay, the positive charge will go to the right side, the negative charge will go to the left side. But of course this is a dipole, you cannot separate them. So it's just like you rotate. Just try to align, 就是对齐那个方向. So all the positive side will point to the right side, will be at the right side, and the negatives, because inside the E field, or I should say inside the E field, okay, for a positive charge, the force will be pointing to the right side. For the negative charge, the force will be pointing to the left side. So the external E field will make the dipole align. So and in that case, if all the dipole align, all the dipole points to the right side, then all this dipole will generate the E field. So I will say this E0 is the external E field. external E field generated by this one and this one, and this E prime is generated by the dipole, dielectric. I mean the dielectric. Generated by dielectric. So this will point to the opposite direction because it's just like this is a positive, this is a negative, so it just looks like a small capacitance. So all the E field generated by the dipole will point to that side. Okay, so it turns out that this is E prime generated by all the dipole with the alignment. Okay, so this E prime will be smaller than the E0. So this is the total. This is the total E field inside the dielectric material. Okay, so this is a very interesting phenomenon. Okay, so 我可以讲一个类比，就是说，你把你们当作是那些dipole， 然后如果不是上课的时候，你们就可能不是朝着这个方向，你们就可能比如说朝着后方跟你的朋友聊天，或者是你随意的移动，去外面倒水喝，或者是去洗手间，或者是怎么样，那你就是一个 random 的状态。但是如果在上课的时候，你们都一般就会就是朝着那个方向，就是上课的状态就好像是一个 external 的 E field apply 在你们身上，那你们都会 generate 朝着那个黑板的方向或者白板方向，就是类似这个意思。Okay, so here we try to describe this thing in a mathematical way. So here it says inserting a dielectric into a capacitor causes induced charge to appear on the face of the dielectric and weaken. So it cancels part of the external E field, but yeah, it is always smaller than the external E field, so it just weaken it, and then the induced charge is less than the free charges on the plate. Okay, so here when we try to when a dielectric is present, Gauss law may be generalized to this thing. Originally the Gauss law is like epsilon naught integration of E dot dA equals Q. This is the original case. If we have some dielectric, then we multiply it by kappa. Kappa is generally like a constant, but sometimes it is not constant. So this kappa, just put it inside. For some of the textbook or some of the material, it will be written like epsilon integration of E dot dA, something like this, or maybe you just put it inside dA, or even making this one to be vector D, but yeah, you just show it one time here, so just you don't need to really care about it. Yeah, so sometimes you just making it like this, D vector dot dA. Okay, so D is like epsilon naught times kappa times epsilon, and some of the textbook it even define it to be a epsilon for different material, but for this textbook you just make it like a kappa and epsilon naught occurs independently. Yeah, so it means that if we have dielectric, we need to consider this kappa here. And of course, just now I mentioned this D. This D is called electric displacement. Yeah, but it only occurs once here and will not appear again. So don't take it too serious in this semester. Yeah, so so here let's try to take a look at a sample problem. So it says a parallel plate capacitor whose capacitance C is charged by a battery. Okay, so so let me finish quickly. So so capacitor C, charged by potential V. Okay, so charging battery is now disconnected and then a potential slab copper is slipped between the plate. What is the potential energy of a capacitor before the slab is inserted? So this is easy because it is just like potential energy. Oh, let me see. So the potential energy is like Ui equals 1/2 CV squared. So 1/2 and then times C is 13.5 times 10 to the negative 12, and then times V is 12.5. Okay, so this number is 1.055 times 10 to the negative 9 joule. Okay, so this is the initial potential energy. And then for B, it asks you what is the potential energy of the blah blah blah. So it still asks you the energy, but after the slab is inserted. So here, C prime becomes copper times C, which is 6.5 times 13.5 times 10 to minus 12. Okay, so this is this change. Okay, so finally, UF should be like 1/2 C prime V squared, or we can use the other one, Q squared over 2 C prime. We use this one because we already changed. So actually, we still need to calculate it. So Q doesn't change. So it is like 13.5 times 10 to minus 12 times 12.5. So this is C times V, and then quantity square. It will be the original Q, but the Q doesn't change at all. And then over 2 times 6.5 times 13.5 times 10 to minus 12. So this is the new capacitance. Okay, so UF will be 1.62 times 10 to minus 10 joule. Okay, you can really observe that the potential energy becomes smaller. Which means that there will be some potential energy change. So it asks you, so you can also calculate that there is some work. The work is like Ui minus Uf. It's like 1.055 times 10 to minus, although it's not asked, but I can just write out. So this is independent to the question, but this value means that you need to do some work. You need to put in the potential slab. And yeah, you may ask, oh, where is the energy goes? Actually, the energy is stored in the dielectric, because you need to make the dipole align. So it should store some energy there. So that some of the energy is actually absorbed by the dielectric material. So you can see there are some potential energy change. Okay, so okay.